Okay, this is re-emphasizing some of the things we looked at in the other book, just from a slightly different perspective on how the climate responds to perturbations, what has happened in the past, and what are the heuristic or idealized arguments we can make so that we know about climate sensitivity and the feedbacks in the system, which feedbacks can amplify the initial perturbations and which will damp the initial perturbation. So you start with this kind of idealized picture where we say, before we did this, where we said there was no greenhouse layer or atmosphere which can absorb outgoing long-wave radiation, in which case sun's energy is reflected from the surface with an effective temperature of 255 Kelvin, which is colder than the average temperature we have now of 15 degrees Kelvin. So obviously that leads us to the argument we made before, that any atmosphere that has the ability to absorb outgoing long wave is going to give us a warmer surface. But how do you think about it in terms of a response to perturbations? Let's say we started with this system and somehow instantaneously created an atmosphere. Let's say Earth formed, there was all primordial soup, continents, etc., and then suddenly enough gases formed to use Earth's gravity to hold on to the planet and have an atmosphere, one layer, in which case at the very instant that it got formed, the atmosphere has to get rid of 238 watts per meter squared coming from the sun, which is going from the surface, of course, because that's what is receiving it, and the atmosphere hasn't adjusted yet, so it will just take the 238 and reflect half of it up and half of it down till it can reach an equilibrium temperature where it can equilibrate the planet at the top of the atmosphere, which happens here after the new equilibrium, new climate is established. So now you have the atmosphere warming up enough to do the sigma T to the fourth, giving us 238 watts per meter squared to balance out incoming sun's radiation. But at that point it's also emitting down 238, and we said the surface then has 476 watts per meter squared to get rid of, and it can do that by reaching a temperature of 303 Kelvin, which is too warm, and we said we have to add multiple layers to reach the temperature that is observed in the current climate. Okay, so think of that here in terms of a time versus energy out from the planet. So you are starting with no atmosphere, so you are emitting all of it back from the surface. Suddenly you add an atmosphere which begins to emit at 120 watts per meter squared, as we saw here, 119. So over time it'll begin to warm up to the energy it is receiving from the surface, because it is receiving 240 and emitting only 120 in each direction. So it's going to keep warming till it can emit 240 to space to achieve the equilibrium. Such perturbations, instantaneous perturbations, do happen in terms of volcanic eruptions, which suddenly erupt. Can be one big pulse of emissions with ash, aerosols, greenhouse gases, and so on, sulfates, etc., but can also happen over several days. But in terms of the climate timescale, it's almost an instantaneous perturbation, like a delta function, as we talk about. And if you remember from before, volcanoes typically cool the global climate, so the radiative perturbation is in negative watts per meter squared. Krakatoa 1883 was a big one, biggest in this record we are looking at. Pele Santa Maria, Agung here in 1961, I think, El Chichon in 1982, and Pinatubo in 1991. And we know from various satellite data how the climate responded, but it's not so easy to prove that this perturbation got equilibrated out before this came in, or this equilibrated out before this came in, and so on. So the effects can linger for a while, but nonetheless there is a fast time scale adjustment in terms of changed radiation coming in because of the aerosols, changed precipitation patterns, large-scale droughts across the globe, and reduced summer temperatures, crop losses, etc. And then there are slower time responses which take a while. Talking about slower times responses in the system, the orbital forcing of obliquity, precession and ellipticity timescale, which range from 23,000 to 41,000 and 100,000 year timescales, can initiate reactions like glacier retreat, which would decrease the albedo because glaciers are very reflective, especially with snow on them, and that would keep more of the solar energy into the Earth system, which increases the incoming energy effectively, and you get more warming, which drives further ice melt. And of course, if there is an initial cooling, then you go the other way where you ice grows, there is albedo increase, there is more energy reflected and more cooling, and ice grows. And we saw that goes much slower because as temperatures cool, atmosphere's ability to hold water vapor reduces, so snow on glaciers begins to reduce, so that goes on for a long time. We are now in a warming phase, so that can be very abrupt, which is what we have to watch out for. And we also saw that when we have n number of layers in the atmosphere instead of one, we get a complicated looking expression for the surface temperature in terms of the balance of energy of incoming solar versus outgoing long wave. So n plus 1 times S times 1 minus alpha, where alpha now is a function of temperature, which it is, as we can see here, divided by 4 sigma. So if you add that temperature dependence, then you can see that you have a more complicated equation for surface temperature as a function of solar radiation coming in and the temperature dependent albedo, which gives us more realistic solution. So the albedo dependence on temperature depends on internal feedbacks like the water vapor feedback, where warmer temperature would increase evaporation and water vapor in the atmosphere, evaporation from the ocean and the surface, and water vapor in the atmosphere. Water vapor is a very strong greenhouse gas, which would further increase the warming and so on. So if you have a radiative perturbation, then the net equilibrium temperature change will be the initial change plus all kinds of feedbacks you have, which can get amplified further. So water vapor change would lead to cloud changes, vegetation changes, and so on, which would give us, let's say, g squared times delta I, which would drive further changes in terms of g cube, where g is a gain factor. It's an amplifier of warming, can be also a damper of warming. That's not what we are saying here, when g is an amplifying factor which can be positive or negative. This can be written in more compactly as delta TF equals k equals 0 to infinity to account for all the feedbacks in the system that are dependent on each other, as g to the k times delta Ti summed over all the feedbacks, which obviously can be aggregated into a net feedback factor g. So then delta TF becomes delta Ti divided by 1 minus g, which is the electrical circuit analogy of amplifying factor, where if g is 0 and there are no feedbacks, then the initial perturbation will be the final equilibrium response. If g is positive, then this is going to get less than 1, and the amplification will be larger because you are dividing by a number smaller than 1. If g is 1, of course, you are going to get infinite feedback. But if g is negative, if there are damping of feedbacks in the system, like the thermostat, which controls AC or heating, then you get a damping of the initial perturbation. The final equilibrium temperature can be smaller. So the key question is, what are these typical major dominant feedbacks in the system? You have the ice albedo feedback that we just mentioned, water vapor feedback, which we just mentioned, cloud feedback, which is complicated, high clouds, high thin clouds, like the contrails from aircrafts, or the high cirrus and cirrostratus type clouds, allow short wave to come in, but they trap outgoing long wave. Deep clouds can create cold temperatures at the top and reflect much less radiation. On a shorter time scale, you can also have blocking sunlight and cooling during the day versus absorbing outgoing long wave and warming during the night, and so on. So it depends on lots of details of the clouds, cloud types, cloud heights, and cloud optical properties, and so on. Right now we can say that we don't know exactly whether cloud is acting as a net negative feedback or a positive feedback to the warming that has happened thus far in the models. That is a key uncertainty as well. Okay, and there is the lapse rate feedback, which we talked about before, where we looked at an unperturbed profile and with radiative forcing of delta Q. If there is no lapse rate feedback, then uniform temperature change can happen. If there is a negative lapse rate feedback, then the temperature would warm less than the upper layer, so upper atmosphere would then, sigma T to the fourth would be larger than at the surface, so you would have net negative lapse rate feedback, whereas if lapse rate feedback is positive, then you would get a larger warming at the surface and a smaller warming at the level where energy is being lost to space. So as we talked about in the band saturation podcast, this is happening, and also the height at which the energy is being lost is increasing as well as the tropopause height increases. So lapse rate feedback right now is probably positive, but again, this is latitudinal dependent, very region specific. We only typically look at global mean and say whether lapse rate feedback is positive or negative. Okay. Solar radiation is another perturbation. Of course, there are seasonal changes which are much larger than these changes in energy output from the sun, which depends on solar activity, sunspots. So sunspots are dark, but when there is a sunspot, there are very bright spot around it called plage, which emits much more radiation. So as number of sunspots increase, sun's energy output actually increases. So you have fewer sunspots, lower radiation, and more sunspots, more radiation. For example, during the last ice age that started around the 1200s and ended at the beginning of the Industrial Revolution, there were several solar minima, which means incoming solar radiation was reduced, which amplified the perturbation end of medieval warming, which may have been initiated by some enhanced volcanic activity and volcanic perturbations and cooling that we talked about. Solar physics is well known. It has this 11-year kind of cycle in its sunspot activity. Judith Lean is one of the leading solar physics experts, and we know now that the solar radiation changes cannot explain the observed global warming, especially in the last several decades, 6 to 10 decades. Okay, you can put that in the context of longer term changes in CO2 as well. You can see that even when the CO2 was very high, well over 5,000 ppm back in 440 million years or so ago, after the Cambrian started, in the post-Cambrian, there were extensive ice ages, so ice existed on the planet. There are various paleo evidences by which you can conclude this. We talked about that a little bit. So there have been several ages, including the current period, where there are glaciers on the planet, like Greenland and Antarctica. And we have talked about how the CO2 in the atmosphere has dropped over the last 100 million years or so because of various reasons like the rise of the Andes and the Himalayas and the drawdown of the carbon and so on. So the level of CO2 doesn't exactly explain the glaciers, because you have internal feedbacks which can take the energy coming in and create conditions, and also depends on distribution of the planets. So the configuration of the continents was different when you go back this far in time, but even in the current configuration, CO2 is low, which seems consistent with the presence of glaciers, but obviously if we keep increasing CO2, they may disappear. So one of the best examples of rapid warming we have had in the history in recent times is the 55 million years ago, the so-called Paleocene-Eocene thermal maximum, where there was very, very rapid warming, as you can see here, and that was associated with very rapid drop in calcium carbonate precipitation in the ocean, which corresponds to increasing CO2 in the atmosphere. So it's not completely understood what drove this rapid warming, but the main thing is to understand what the climate sensitivity is to a given perturbation. You can back out the CO2 or methane needed to do this kind of rapid warming, and there are hypotheses like release of methane from hydrates that are buried in shallow waters under high pressure and cold temperatures. But that remains open. The other question is, are we warming this fast or faster? And it turns out that from all the evidence we can gather for this period, we are now warming since Industrial Revolution much faster than what happened during Paleocene-Eocene thermal maximum. Of course, we are increasing CO2, and that's a different driver than what would have happened here. So we have to be careful about that as well. So let's leave that here, just again re-emphasizing some of the points we looked at before from a slightly different perspective, and we will again look at the impact of humans, including population, affluence, and technology, which we looked at on emissions and global warming in the next podcast. Okay.